Саша, это Максим говорит, ничего не слышно.
Добрый вечер. Слышно хорошо? Может, поближе.
Скажите, пожалуйста, слышно?
Ну, пока слышно.
Профессор Си, так что который нам поступал. Я вижу. Нет, я ничего. Да, Ну, все подсоединились, кто хочет. You can, here you found the link. I think it will be more convenient to join. Or maybe you can look at here. Yeah, this is just the same. Okay, let's start. Okay, let's start the seminar. I'm glad to present our professor Г.Б.Шабат. We will speak about the self-generated commutative rings of commuting differential operators.
Thank you for the introduction. Recently, there were some reasons for me to return to my activity that took place more than 40 years ago, but I found it interesting enough and hope to continue it now. So sorry for telling you mostly about very old stuff. And maybe we'll find something new. The main part of the talk is going to be just calculated with some geometric comments. Now, here is the plan of the talk. Sorry, I wanted to apologize for the first error in this talk. It is April 11 now, as perhaps everybody knows. I plan a rather long introduction into the subject. Maybe it is very well known to the participants, but anyhow, the story of this domain doesn't seem to be complete, and I think it is useful just to look at the origins. So it started long ago, as you see, and in the beginning, the activity in this domain took place in the pure algebra and pure differential equations, and the experts did not communicate usually. So as I give here a list of the most important papers, as you see, usually they did not quote each other and seemingly were unaware of the results of their procedures. I can tell you a real story of Moscow mathematics of 1970, perhaps before most of the people here were born, and the theory of commuting differential operators turned out to be quite fashionable. Moscovites first, most of them perhaps first in their life, heard about Cartesian de Vries equation, though of course everybody knew that it is exactly the same equation as twice differentiated Weierstrass differential equations that everybody knew. And it was a sensation of some kind that the stationary KdV was equivalent to the algebraic problem of commuting over certain differential operators. So sorry, I spoke about it before. I have shown the corresponding slide. So these are the first general papers on the subject, and Krичевир, the author of the first of them, was originally the topologist. Unfortunately, he passed away recently. He was a student of Novikov and originally a topologist, but at that time he already became an expert in differential equations. And as for Greenfeld, he was a student of Manin, and the same as it was with me, and was a very pure and abstract algebraist or algebraic geometer. However, their results, though written in the completely incompatible languages, had the same subjects. And what these people, these classics, wrote about nonlinear equations was much more general than the specializations that the people were interested in at that time. Now, before discuss that, let's introduce some notations. And I myself is, as I said, come from algebra. And well, it is quite natural for me to work over an abstract field. Here we assume that it is algebraically closed. But if one is not in a mood to think in some abstract way, please, you are free to consider the ground field as just the field of complex numbers. Now, everybody here, of course, knows what differentiation is. Here it is. This broken line is just explained by the default agreement of algebraic people. Since the pair K calligraphic is an algebra, a usual arrow would mean the morphism in the category of algebras, but it is not a morphism of algebras, since it does not respect the multiplication there, but satisfies the Leibniz rule instead. So given a fixed differentiation, we construct the non-commutative ring of differential operators, and there is a condition of so-called ellipticity. To make the things lighter, we just assume that the leading term of the operators we consider is 1. A bit more complicated theory demands that the leading coefficient is just invertible in the function field, this K calligraphic. So we define, of course, the order of the ordinary differential operator, and to make the things more down to earth, we introduce some separate functional space on which, instead of the main theorem of ordinary differential equations, we just assume the statement about the dimension of the kernel. So every operator we are considering just has of order and just has an n-dimensional kernel.
Do you assume that the field is of characteristic 0 or not?
Field of constant is yeah, sorry, I'm not sure that I didn't write it down. Yes, sorry, of course, I assume that here we have the constants in blue. So
Yeah, but it's of characteristic 0, right? Or not?
No, I didn't mean that. And a very interesting case is when the differential field is the field of piezo series over any field at all, over another algebraically closed field.
Yeah, what they call Monica's algebra.
Piezo is the ring can be defined in 2 ways. Either it is the algebraic closure of the field of rational functions in one argument, or in fact it can be called the field of Newton piezo, because there is a nice theorem that constructively the piezo series is a Laurent series in fractional powers of the main variable. Fraction means that for every element we choose the common denominator and write down the Laurent polynomial in the corresponding root of. Sorry, I don't really understand. If I use.
Yeah.
Oh, okay, great. It is seen, yes. So the piezo. It has a standard notation like this, and it consists of the expressions like this. A sub I x2 I over d from a, that means with only finite number of negative indices, and it means that, well, d is fixed for any series like that. And in fact, Newton knew that this field is algebraically closed as soon as some I belongs to K, and when K is algebraically closed, this field is its algebraic closure. Now I can write it down. This here is distribution. Newton, of course, used another language, but he explained how to explain that it is isomorphic to the algebraic closure. He explained how to solve the polynomial equations with rational coefficients.
So, formally speaking, that's kind of Galois theory, right?
Yes.
But without Galois.
What do you mean without Galois?
I mean,
The Galois group of this
yeah, I mean,
this field is one of the most tantalizing groups.
yeah, I understand. I mean,
And there is an expert in it, Marat Ravinsky.
I mean that you can solve any equation. Yeah, that means that.
Yes.
That means that Galois group is
Yes.
probably.
It's Galois theory about 200 years before Galois.
Yeah, that's what I said.
So that's it for the notations. Now the next slide perhaps means something obvious for everybody. Here, our commuting of the differential operators perhaps is not really used in the ring of differential operators, but rather is used in the functional space. So I think that the facts that are written here are obvious to everybody here, and as soon as we have two differential operators, this system of differential equations written down in red is the main subject of the investigation. Now, here is the meeting of algebraic geometry and differential equations. So the effect formulated in blue is kind of tautological. I don't think that any comments can make it more obvious as it is written now, though, well, when I started doing it many years ago, I first checked it for several cases, and I'll show the calculations, and then only then it became obvious for me. Now there is a small trick. The two commutative operators are quite symmetric in this story. However, we can choose one of them and consider the action of the other on the eigenspaces, on the general eigenspaces. Here we choose the eigenspaces of the operator M. Let me remind you that it is finite dimensional by our assumption, or its dimension is equals the order of M. And this high of M is called a spectral curve. Again, this is kind of another main hero of the story, and the who not only differential operators, but the whole ring of the differential operators commuting with them are restored by L. So it is written here in the algebra geometric slang. Sorry, perhaps I should formulate before the classical result mentioned several times in 20th century in the papers from which I started the talk. That is any differential operators that commute with two of them constitute a ring. It is not a property, not a purely algebraic property. You can easily find examples among the matrices where this principle breaks, does not hold. So what is written here, however, is that we consider the who polynomial ring of two letters, lambda and mu, factorize it by this equation and get the affine curve that the polynomial ring of the coordinate ring of the affine curve that is the spectral curve. So the slide, sorry, was on the previous slide. Excuse me again. Here I should assume that the orders of L and M are coprime. Then their common eigenfunction is defined uniquely up to the multiplication constant. And well, again, using some simple simple algebra, you can check that the original differential operators satisfy the same equation as the spectral curve.
It's some kind of Kelly-Hamilton.
Sorry?
It's some kind of Kelly-Hamilton.
Yes. What I said about simple algebra is called exactly this. Now we turn to the particular cases, that is, start the simplest orders, that is 2 and 3. This is the question. Sorry, I again skipped the details concerning the order next to the leading coefficient. It can be killed in the same way as with algebraic equations by simple transformations. So we just start with Sturm-Liouville. and then ask ourselves when does the operator of order 3 exist commuting with it. Sorry, I didn't ask what is your tradition in terms of time.
1.5 hours.
90 minutes. I was.
Good. So here is the answer. And here is how the stationary KdV appears, the equation I mentioned in my introductory words, and it is a result of a rather easy, straightforward calculation, but here and perhaps almost everywhere in the future, I omit the constants of integration. In fact, well, I'll show you in the next case, perhaps, that the actual integration of this nonlinear equation, this is a nonlinear equation in the coefficients. But it turns out that P and Q are differential polynomials in terms of U, and at every step we meet a small gift of nature, because you find the derivative of a coefficient of the differential operator, and it turns out to be the complete derivative. Therefore, you gain the integration constant, and this is what I omit here. Now, what is really interesting here in this example, in which the calculation part is easy enough. In fact, can be made by hands. The spectral curve appears in two ways. That's the first way is just here. You see it, you make the corresponding calculations, and here it is. By the way, the classical solutions of KdV that come from shallow water correspond to the case of the degenerated elliptic curve, and therefore are expressible in the elementary functions, in the hyperbolic trigonometric functions. However, if it is the general curve, the answer is formulated in terms of elliptic functions, and look, in integrating these coefficients, you get some expressions in again this so the date was not the only mistake. Sorry, you should I'll write the correct integral just in a while. The correct U cube in at 1/4 you should read U cube, and then check that the derivative of this polynomial is constant, is zero due to the stationary Cartesian. The same is about I2. So this is a real, this is a true elliptic curve that does not depend on any parameter. However, here it is profitable to think about the classical case and use some transcendent approach. In fact, we have to do a small renormalization in such a way that the stationary KdV becomes just the Weierstrass equation. Again, I said it before, without the equations. Here in the small letters, I remind the basics of elliptic functions. They are related, and the coefficients of the Weierstrass equation are related with the integrals in a very simple way. And sorry again, I didn't say perhaps that though the psi, the common eigenfunction, is defined for any lambda and mu up to a constant, its logarithmic derivative is well defined, and it is a rational function in the product of spectral curve that is represented by the spectral coordinates lambda and mu here, and the function on the curve. And this formula is just its true interpretation is just in terms of the uniformization. So the P function, P and P prime, defines the uniformization of elliptic curve by a complex line, and the pole of the logarithmic derivative of psi function just moves linearly in this curve with respect to the time. The time is something abstract. Perhaps the best thing here is the best thing is to think about the time as about the uniformizing parameter on the copy of the spectral curve.
Sorry, what does MERC means?
What does what?
There is the first line of this slide, there is some abbreviation which is not familiar to me. K is equal to C, K and F are equal to something like that.
Meromorphic functions.
Meromorphic functions.
Mhm.
You know, the abbreviation.
Mhm. Now, the next case that was also analyzed thoroughly in the 60s and 70s, again, is the pair of 2 and the next odd number. Now we just look for the operator of degree 5. So the answer is the higher degree. It is here. And perhaps I'll finish the comments about this slide and then perhaps demonstrate you the direct calculations just to to try to persuade you in the simple fact that the straightforward calculations in this domain become very involved even in these simplest cases. Now, what the bottom lines tell us here. So, as for the other answers, in fact, there is some other information when we want this problem to be solved completely. Then, as for geometry, unfortunately, I'm unable to explain it in a non-technical way. But here the common eigenfunction has two poles, and these poles travel along the symmetric square of the curve of genus 2. Now, this symmetric square is very close to the Jacobian of the curve. And from this point of view, the direct formulas just show that this moving along the Jacobian is straightforward in terms of the algebraic structure of geometry. And now there is a universal way to check it in the style of Novikov's school, or maybe generally in the style of the experts in completely integrable systems. To the best of my knowledge, there is still no general definition of a completely integrable system, and there are several non-coinciding levels of this concept. But technically, I would suggest to call the completely integrable system the one where in some coordinates the solutions can be written in terms of theta functions. And you can find the solution of this problem in terms of theta functions in lots of sources. One of them is the Mumford's book about theta functions, where a special technique is developed for the hyperelliptic curves of any genus. However, if we just do it straightforwardly, it is not so easy as well. Now I'll try to show you the maple calculations. Then I share screen and what's wrong with my file? Excuse me, it was prepared very well. Unfortunately, I do not see what. Well, let me just find it. I hope it works. Here is the seminar. You don't see what I'm seeing because I don't share anything. Yes, now I press my Maple file, and sorry, it takes some time. As soon as it appears in my screen, I hope I can share the screen sharing. Yes, here it is. And now, should I stop share perhaps first? Yes, and then share screen again with the hope. Yes, I hope you will see it now. Do you really? Good. So what we see here is exactly the pair of equations for the two commuting differential operators of the powers 2 and 5. And now we calculate, and what is convenient is in Maple is that I can hide the technical part of the calculation, that is, calculate the product in one order and in another, and then hide it again. And here's what we have. These are the expressions for the coefficients in terms of the only function u that defines the differential operator of order 2. And everything is defined in terms of it. And here are the expressions for the action of the differentials on the psi functions. And finally, we get this analog of this exact formula for the logarithmic derivative of the common eigenfunction, and again it is rational in u in the coefficient of Sturm-Liouville function, and algebraic in lambda and mu. And this is the purely algebraic picture of this behavior in set of functions that is so easy in set of functions. Now I'd like to, there was a question about characteristic here, and I'd like to speak a bit about the arithmetic of these coefficients. As you see, there are some properties that are immediately obvious. The special role of the primes 2 and 5 in all these expressions. What does it mean in terms of arithmetic? A very simple way, a very simple thing, that the behavior of these objects modular 2 and 5 are quite special. For example, the M degenerates modular 5. it means that it reduces to something like the commuting of just the powers of differentiation in the 5 adic fields. So, well, I share this obvious observation, but I should confess that I did not think about it precisely in terms of the 5 adic fields, but I'm sure that it should be done. So this is, in fact, this is, no, the last thing I have to show is the set of integrals. As you see, the polynomial integrals of the second KdV. As you see, they are rather long, and as perhaps so I was showing that just to persuade you that the straightforward calculations are rather wild activities. Here is the answer. And of course, lots of people, among them the great ones like Gelfand, Shubin, Manin, and others. No, I'm sorry, I don't really know who is who should get the most credit for constructing the KdV hierarchy. So we have looked a bit for the first two elements of it, corresponding to the second operator of orders 3 and 5, but there is an infinite sequence of them, and they all constitute a nice and highly non-trivial object. So that's all. Perhaps before I close this maple file, I rather ask the participants whether there are questions about it, because I won't like to open it again. Since there are no questions, well, we can do it after the talk anyhow, and now we have to find the and now again, Control, what should I do to find myself in the full screen demonstration? I really don't know.
You are already in the full screen demonstration.
Okay, it is. Well, everything seems seen. So the original talk starts just now, because sorry, I did not mention the motivation of my calculations made long ago. I wanted to apply these the relations between differential equations, the geometry of differential equations and spectral curves, in order to clarify some points about algebraic geometry. And then the KdV of all the orders turned out to be insufficient because they cover only the case of hyperelliptic curves. Now, the simplest case that is not hyperelliptic is the case of this set of orders. And here are the straightforward calculations. So since this paper was published in 1980, it follows that I was performing the calculations by hand, and I think it took me several months to get all of them. So here I do not omit the constants. You see the precise result of these calculations, and we have the over-determined system of equations. Just in we get 4 differential equations in just 2 unknown functions. So this is an over-determined system of differential equations. However, we know basically the dimension of the set of the solutions, the dimension of the the set of the solutions. We could think about it as about well, some affine manifold with the polynomial vector field on it, and it has some polynomial integrals. How do we know it and get the information about the set of solutions? Here we need some algebraic geometry that I perhaps better formulate in words. It was the, let me see whether is, there is an explanation on the next slide. So I'll show you the next slide. But as for pure algebra, the following happened. Now I want to move this technical side. So just to struggle with these 4 equations, we perform these transformations. And at these 40 years ago, they were found by intuition, or rather considering the degenerate case where the operator of order 4 was the square of the operator of order 2. Anyhow, anybody can check that performing this transformation, we come to the system with the following enigmatic phenomena that are written down in blue.
May I also ask a question before?
Yes.
You obtain 2 operators of degrees of orders 4 and 5, which can be given operator for the first operator. Do the separator can be divided in themselves?
Do the order?
Yeah. The order 4 and order 5.
It was a general theorem of that, and it's and other people that yes, it has nothing to do with these particular orders, but it is the general algebraic fact. Yeah. So And now perhaps I have to say something about these words. The contribution of Drinfeld in this theory was strange enough. I mean, the first thing he noted was close to trivial. That is, and I'll try to explain it without notations. So instead of considering two or more commuting differential equations, let's work in a more invariant way. Consider the ring generated by them, that is, the commutative subring of the ring of differential operators. Now, there is it is natural to consider this ring separately, this commutative ring, separately from the ring of differential operators. So we take an abstract commutative ring. In this case, it is an affine ring on a curve, on a smooth affine curve. And as soon as we map it into the ring of differential operators, we get such a function on this ring, the order of its image. And well, at 70s, you should be Drinfeld to notice that this order is nothing but the valuation of the field of rational functions on the smooth model of the spectral ring. Therefore,
What is
the order,
Yes.
so we map an abstract commutative ring into the ring of operators. So every element of the ring becomes a differential operator. It has its order. It has its order, yes. The orders of the product multiply, and the orders of the sum do not exceed, are, yes, no smaller than the smallest of them. They are the valuation of the ring, and that means that they are the valuation of the field of fraction of this ring. Anyhow, it is a point on the spectral curve, where now by a spectral curve, I mean not just its affine model, but rather a smooth projective model. So it is my suggestion, of course not Drinfeld's, to call this point a Drinfeld point of the commutative ring of differential operators. And now we can use some small differential geometry to understand that the previous example of the orders 2 and 5 correspond to the curves of genus 2 where the Greenfield point is is the Weierstrass point.
What is the point again?
Greenfield point is the point that that defines the valuation. We have just defined.
Variation is a point.
Well, in abstract algebraic geometry, the point of an abstract curve is nothing but the valuation of field of rational function, of the field of rational functions on the curve.
Sorry, I'm quite familiar with this thing.
So the previous case corresponded to genus 2 curve with Greenfield point being one of the 6 Weierstrass points. And here with the degrees 3, 4, 5, we have a genus 2 curve. In a while, I'll explain why we can immediately see that it is that the spectral curve has genus 2. Oh, let me explain it now orally. One of the forms of Riemann-Roch theorem tells us that the genus can be defined in terms of the so-called Weierstrass gaps. Here we just look at the monoid, additive monoid generated by 3, 4, 5, and count the natural numbers that are not in this monoid. They are precisely 1, 2. And the number, according to Riemann-Roch, the number of these Weierstrass gaps is precisely the genus of the curve. Then by the joint efforts of, I would say, at least Krejcimir and Greenfield. Well, I'm sure about Krejcimir because my late brother at those far years was quite surprised that his activity in differential equations led him to study algebraic geometry, and told me what he knew about algebraic curves, and was sure that this theory defines some special kind of curves. And he was quite surprised when he learned from Krejcimir that any curve participates in the story. So we know that here with the degrees 3, 4, 5, we'll see all the curves of genus 2 with marked non-Weierstrass point. This is more or less what is written here.
What is non-Weierstrass?
The genus 2 curves possess the involution with 6 fixed points. These six fixed points are Weierstrass ones. All the others are non-Weierstrass. Yes. So it is now here in black you see some explanation of the miracles of my calculations of 1980.
Only one remark. Here this genus this is not only as an arithmetic genus. A priori, we don't know if this curve is not singular. Might be singular.
What do you mean by this? Oh, yes, yes. When we calculate with given functions, we consider the general case. as for the inverse problem given the curve, we just consider the general case. It is really a very nice
And
question.
even if you are looking for three commutative operators of what is 3.5, it happens that the curve is singular if the coefficients are not generic.
Yes, no doubt in that. Yes, and by the way, what I'm doing now is writing a paper about my late teacher Manin, a long paper, and I have found his paper exactly about what Sasha remarked. Maybe you know it, the matrix solitons and so on. And I think Manin gave a very good reason to consider it geometrically. He claimed that the degenerations of the general solutions are very difficult to analyze in terms of theta functions, but much easier to analyze geometrically. So I was surprised to find out that perhaps there are only 4 references to this paper, but maybe the time will come when this paper will be read. Now, as for the explanation of that miracles I have chosen you, we need again some pieces of algebraic geometry of curves. Where do the simple relations between the coefficients come from? The curve of genus 2 can be realized in the traditional Weierstrass form, but there is another realization if we realize by the functions that have their poles only in one point, like in our case, then there will be functions of with the poles of order 3, 4, 5, and they embed the curve of genus 2 in 3 space, in the projective 3 space. Again, Riemann Roch can help you, and they are quintics. You can ask how do we get the curve in 3 space that has the prime degree. If you want to get the curve of genus of degree 6, you just intersect the quadric and the cubic, and the general intersection will have a genus 4 and of course the degree 6. But it can happen that the intersection is not really generic, because the quadric is full of lines on it, and the cubic has just 27 of them. But sometimes they can coincide, and then this kind of intersection of cubic and quadric is this line and a curve of the remaining degree 5. So any curve of genus 2 can be obtained by this construction, and it depends on the choice of the original non-Weierstrass points. So this is the explanation of that substitution. Well, now I'm close to the end, as I should, and there is a reasonable question: what happened during the more than 40 years with this subject? The answer is almost nothing, but what was miracle? A miracle now has its simple and natural explanation, and I'm not ready to discuss the interesting particular cases. I have to look through the literature then, and I'll be obliged to anybody who shows me some considerations over the arithmetically, say, the Q bar differential equations. And here is a list of suggestions that I discuss briefly for the remaining 6 minutes. So first, as I have shown you a bit, the straightforward calculations are stupid and just cover the simplest cases with great difficulty. It can happen that perhaps there is some special language for special tools for working with differential algebra. Sorry, I know that they exist, but never worked with it. I know the people who study the Galois theory of linear differential equations. But perhaps a more wise way would be to do what was done in the KDV text, in the KDV case. So instead of the stupid direct calculation, just take the pseudo, the formal pseudo differential like this. Again, some algorithms are needed to calculate the coefficients easily. And then take its powers and the positive part of the powers of these pseudo differential operators. To begin with, of course, one should repeat the calculations I did in this with this technique and compare what is easier. Now the next case is, in fact, our 345 case is the intersection of two cases. So we can consider them separately. And now again, so here is the case of the commutative ring. My talk is called 3-generated ring of differential operator. But there are 2 generated. Here we consider the operators of order 3 and 5 and 4. Then we get 6 as 3 plus 3, 7 as 3 plus 4, and we are done. So we have just 3 gaps here. So this is the theory of curves of genus 3, but embedded not like in the classical case, not like a quartic in the projective plane, but just like with the linear system concentrated in just one point. And the same thing is happens here.
What does mean linear system? What's a good example?
It is what I said in a common language is that we generate or better just embed the curve into some projective space by the rational functions having their poles only in one point. So here we have 3 and 5 again, and the gaps are like this, and this is the curve of genus 4. Again, it is embedded in some non-traditional ways. So our construction, and well, in both cases, we work with the moduli spaces of curves of genera 3 and 4 with one marked points, and our algebra-geometric case with 3, 4, 5 sits somewhere on the common boundary of these moduli spaces. So here we meet, in fact, the second geometric problem. As for the first, we discussed it several minutes ago. I mean, consider the generalization, the degenerations and singularities. And here we also find something on the boundary of the curves of a larger genus. So this is a purely algebra-geometric task. I'm sorry that during 40-something years, I didn't find time to analyze it. As soon as I pronounce it, it sounds quite interesting for me. Now, there is perhaps just a result of my ignorance. We parameterize our objects by two kinds of numbers: initial values of our functions and constants of integrations. When I don't know how their what is the difference between the role in the algebra geometric realization. Now a very general plan was really our joint with my late brother, and the discrete analogs have a very clear shape. Just instead of one Greenfield points, we have two of them, and the difference operators also define the spectral curves. I believe that the dynamics, that there is a discrete version of the dynamics that perhaps I should call, I don't know, Krichyshvili dynamics or Krichyshvili-Novikov dynamics. I should ask the experts. And finally, there should be more arithmetic that well, shows itself in many ways. So thank you for your attention.
Thank you very much. Are there any questions?
Here is stupid question, because I remember when I talks by, I think it was
Maxim is here. He's in
Yeah, I remember that in the Schneider mentioned that one of the best papers for the feature joint in the feature was about differential operators, commuting differential operators with non-coprime points. So is there anything you can say about this case in language?
Well, it is the algebra-geometric part of it is totally different, because here the common eigenfunctions constitute the linear the linear fibration over the curve, and it is the theory of such linear bundles was in fact clear in 19th century. As far as I can, well, I look through the literature in the non-coprime orders of the differentials, we have the multidimensional vector bundles over the curve. Anyhow, well, this theory is also classical, and Andrea Weil called the matrix divisor, but they don't have this clarity of classical Jacobians, integrals, and so on. So it is a much more complicated part of the theory, but there are experts, and I believe such as Jacob is one of them.
Yeah, maybe.
You could ask him.
I have one question. You mentioned one paper of mine. Which of what is the paper? It's a big 100-page paper or not?
No, it is quite short, published in Gelfand's functional analysis with these. I'm sure it can be found by the keywords matrix solitons.
Of which year? Of which year? You remember?
I'm just writing about it, so it's easy to check. But I think 78 or something.
Okay.
Hi, sure. Professor Shabbat.
Yes, can I see the person who speaks there?
Professor C.
I should stop share perhaps to do so. Yes.
Hi.
Yes. Hi.
So yeah, I like your story because so can you tell me, like, you have the equation 1 to 4 and also equivalent like 5 to 8, and the do you know, like, the you said it's a rational variety, and what's its dimension of this rational variety?
You mean after all this rescaling? Well, I don't remember, but it is just easy to calculate because there are 3 parameters for the curves themselves, 3 times 2 minus 3. Then there is 1 parameter for the non-Weierstrass point that gives 4, and 3 parameters for the initial value where the dynamic starts. So I think the answer is 7.
Okay, so actually, I think so I find this quite interesting because you see, like, Yuji and I, so accidentally we think about this problem from a very different point of view, but we construct like a 2-parameter of solutions for this system of equations. So we actually construct like 3 differential operators of order 3, 4, 5, and show that they commute, and also find out their spectral curve. It's in projective space, but it's a singular one, like associated with the soliton solutions of Boussinesq.
Thank you. I've got, thank you very much. I've got a letter from you with perhaps with that paper. Sorry, I didn't answer and had no time to open it, but of course I'll read it attentively and write you what I've got. It is very nice for me that somebody else is doing the close things.
Yeah, that's yeah, it's a pity that we didn't notice your paper before, but I feel like quite happy that this is already, you know, in 40 years ago, someone already like interested in this kind of thing. Because when we have had this result, like it's kind of hard to propaganda. Yeah. So we have some like construction, not even for like 3, 4, 5, maybe like even more generally, like for example 3, 7, 8, and we can construct like differential operators of that order, and they mutually commute. Yeah. Right.
Well, for me, the order is, as I've said in the last slide of the talk, that first I'm going to find more advanced ways of calculation and then try more examples.
Right. Okay. Yeah, we basically we care about the same kind of thing. Like it's kind of hard to get the degeneration of theta function. So we use some kind other method. Yeah. Thank you.
Welcome.
Yeah.
Are there any other questions? Sorry.
Okay. Are there any other questions? I hope everybody can. I remember that you told me before about some recent talk about this discrete case of different separators. Do you have something new since that?
No, there is a main reference, Mumford and somebody, a very long paper, I think, of 60s, where the whole machinery of these infinite metrics with non-zero elements only close to the diagonal, and well, I think the understanding of the algebraic part of the story starts with this paper.
Okay, so let's finish the talk for today. Now, the probably discussion we can continue. So thank you very much. Thank you everybody for coming. Bye. Have a good night. Хорошо.
Возможно, еще раз погромче.